everyone, so this is problem set 8. I recommend that you start working on this separately and then watch the video to check your answers. I'm going to quickly go through the answers. So if you have any questions, let me know. We'll start off with question 1. So with this question, they want us to figure out what graph goes with the centripetal acceleration versus the speed. What we're going to do is we're going to use the equation for centripetal acceleration, a equals v squared over r. According to this, the relationship between centripetal acceleration and velocity is a squared relationship. So we're going to pick the squared graph right there, C. Question 2. Here, we end up having essentially kind of like a plug and chug question where they are looking for the acceleration and they say that they want it in terms of g, but I'm going to worry about that later. First, let's take the equation for centripetal acceleration. So AC equals v squared over r. They give us the speed to be 14 meters per second. That's going to be squared. And the radius is going to be 10 meters. So when I plug this all in, I'll end up getting, what is the answer? We'll end up getting 20. So that's what the acceleration is going to end up being. Instead, what I want to do is, in order to get it in terms of g, I'm essentially going to divide this by 10, and I end up getting 2 g's because 1 g is 10 meters per second squared. All right. Over here, so we have again, it's another one of these graph questions. This time they want the graph for centripetal acceleration as a function of time. Now, of course, it is extremely important to make sure that you're constantly checking this term. I probably should have mentioned that for question 1, that the speed, you want to check to see if the speed is constant. In question 1, the equation, the graph was based off of speed, so that didn't matter. But here, this actually does play a part. As long as because the centripetal acceleration is based off the velocity and radius, if neither term is changing, that means the acceleration is not changing. Therefore, acceleration should be constant. All right. Number 4. So here we have an object that is experiencing a centripetal force. It's traveling in a circle, and they want us to figure out what's going to decrease this centripetal force. So the equation for a centripetal force is Fc equals mv squared over r. So going through all these choices, the direction of the motion doesn't change anything. These are all numbers, so we're just going to plug them all. Like as long as these numbers don't change, the value doesn't change. So direction doesn't matter in this case as far as the value. Mass, increasing the mass would increase the force, so it can't be that. Increasing the speed would also increase the force. Therefore, it's the radius. If we increase the radius, we will decrease the force because they have an inverse relationship. Oh, I did not realize that I put a square on that. It's mv squared over r. Sorry. Number 5. So another question where they have the ball spinning around in a circle, and they want us to figure out if the string gets released, at which point should it be released in order to hit the target. The best way to do this is to figure out which one would have a straight line distance or a straight line path towards the target. Keep in mind that as the object spins around, it will always have a velocity that is tangent to the circle at that point. And once it releases, it will follow that tangent line. So at A, it will go straight to the right. At D, it will go straight to the left. That should have been straight to the left. This would go down at an angle. So the answer is B. B is the only one that, when you draw a line tangent at that point, is directed towards the target. All right, now this one's a little bit tricky because I don't think I explicitly mentioned the concept of average speed, average acceleration in terms of circular motion. So we have a car going around in a circle, and here it's starting at rest and then ending at rest, which is a bit weird for these types of problems since they don't normally have an object changing its speed, as of now at least. When they're going into circular motion, normally circular motion is constant speed. In this particular case, this is actually one of the few examples of a fairly old AP style question. Remember, that's what the 5 choices means, that these are more AP style questions, while the 4 choice questions are regions questions. So if we're going around in a circle, we're starting at 1 point and we're making 3 full revolutions. That means we know that our total displacement is 0 because we're starting and ending at the same spot. So all the ones that say that one's got to be an answer has to be correct. Now, the next question says the average speed is 0. Now, the thing is, because they're specifying average speed, this is not going to be true. Um, the reason for this is that average speed is distance divided by time. So because the car is traveling a distance in this certain amount of time, it does have an average speed. The average speed is not 0. What is 0 would be average velocity. The average velocity of this car would end up being 0 because of the fact that it starts at rest and ends at rest, and we're assuming that it's going to be fairly linear as far as a transition or uniform transition. So because they specified average speed, that one's not going to be true. So 2 is out of the running. Nope. And this is something to kind of always keep in mind. Whenever they say average speed, a lot of times that is going to be a big trick. Is that it may be true for average velocity, but not necessarily average speed, or vice versa. Now, as far as the average acceleration, because that's going to be the determining factor of which one of these is actually correct. Now, the thing about the average acceleration is that when you are moving in a circle, average acceleration is 0. The reason being is that for every time you're on this side of the circle, I'll just make my circle. Every time you're on this side, your acceleration is down. And then when you come down here, your acceleration is going to be pointing in the opposite direction. When you're over here on the circle, your acceleration is pointing inward. Your acceleration is pointing inward on the opposite side. So for the most part, as you're going around the circle, there's always a point opposite on the circle where the acceleration is theoretically going to be equal and opposite to that. Now, it's going to be a bit weird for this because of the fact that the speed changes, but we can assume that, again, as the speed should be changing uniformly, that this should still hold true. So the answer is 3. I will say that this one was tricky, mostly because of the changing speed aspect. If it was constant, it would definitely, there would be no question about whether or not this was 3 was correct. Now, number 7. So this one's the 1-1 method question. So number 7, we have we want to figure out what happens to centripetal force as the speed ends up being doubled. So again, we look at the equation, Fc equals mv squared over r. Mass is staying the same, radius is staying the same, but the speed is being doubled. So it's going to be 2 squared over 1, which means that the answer is going to be quadrupled. All right. Down here, so another region type question. As the object goes around in a circle, which path would it hit when it hits point B? The idea here is that because of this ice, the object loses that centripetal force. It loses the friction force that is keeping the car in the circle. So it will not continue through path A because there's no more force acting on it, or at least the force is so small that it can't keep it in the circle. So just like we did for this, actually surprising for this question, number 5, once it hits point P and it stops being in the circle, it's going to move in a straight line in that tangent path that it would have ideally done, without that centrifugal force. So the answer would be B. All right, number 9. So another one of these questions where they want us to figure out which one is the accurate statement. We have an object moving in a constant circle. The net force on the object is 0. That doesn't make any sense. We know that that there is going to be a net force on the object, because remember, even though it's moving at a constant speed, what matters is that the velocity is constantly changing. The velocity is changing directions. Therefore, the object can't be in equilibrium. So one's all out. The acceleration 0, again, for the same reason, because of the fact that there's got to be a net force, then the acceleration also has to be there. Keep in mind, it is extremely important to make sure that you remember that net force and acceleration go hand in hand. So if one of them's 0, the other one's 0. If one of them's constant, the other one's constant. So they have a concrete relationship between each other. So because one is out, 2 is also out. So you could have also actually done that. That could have been another aspect. The fact that there were some choices where you could have one or the other means that those couldn't be it. So from there, we actually see that the answers, none of the above are accurate, because the only one that's correct is choice or choice 3, option 3, or statement 3. That's it. Statement 3 is correct, but none of these choices actually had statement 3 only. All right. Here again, another one question where they want to see which one gives us the greatest increase in the centripetal force. So because of the equation, mv squared over r being equal to the centripetal force, there is a inverse relationship with radius. So we want to be decreasing the radius if we want to increase the force. So having the radius would be one thing that we want to do. And then as far as velocity, it doesn't have a direct relationship per se, but is proportional to v squared. So as velocity increases, so does the force. So we want to increase the velocity. So increase the velocity and decrease the radius. Number 11, so they want us to figure out what the centripetal acceleration is. This is one's another plug and chug. So ACE equals v squared over r. 4 squared divided by 0.25. Nope. So then the answer ends up being essentially 4 cubed, I guess you could say. So the answer is D. All right. Number 12. So we have a force acting on the object, blah, blah, blah. They give us numbers, plug and chug. Nothing crazy here. Fc equals mv squared over r. So we have a 40 Newton force, 5 kilogram object. We're looking for the speed. The radius is going to be 2. So putting this all together, we're going to end up getting D, 4. All right. All right. So this one is a tricky question. All right. So it says the centrifugal force felt by the object in uniform circular motion, and they give us all these things, and a lot of these seem like they make sense. Like for example, uh, you might the whole idea for this question is that they're banking on you accidentally confusing it with what we keep calling the centripetal force. Remember, the centripetal force is the force that pulls an object in towards a circle, right? It's what keeps an object moving in a circle. We know that the centripetal force is always directed towards the center of the circle, um, and is inversely proportional to the radius of the circle. So that's all. That's all kind of related with centripetal force. So those two are actually thrown out. So what is centrifugal force? Now, there's a lot of videos that talk about this, and you might get slightly different responses depending on what videos you watch, because technically it depends on your frame of reference. Don't worry about it. That just over complicates the problem. The answer is there is no centrifugal force. So the answer is it's 0. The idea for this is when you see an object moving in a circle, so let's say we look at an object that is on the gravitron, right? So this is us standing on the gravitron, and we're watching a person being pushed up against the wall of the gravitron. From our point of view, if we're inside of the gravitron as the person's moving around a circle, that person looks like they are at rest. They're in equilibrium. So the idea is, well, if this person's staying at rest on the wall, if there's a centripetal force pulling him into the wall, then there must be an equal and opposite centrifugal force going out. In fact, centrifugal means away from the center. So centripetal means towards the center, centrifugal means away from the center. So the idea was that there was this equal and opposite force balancing the centripetal force in order to keep the object at rest, because objects at rest must be in equilibrium. But the whole idea is that you're looking at it in the wrong way, and you have to look outside of the gravitron. When you look outside of the gravitron, it makes sense that the object doesn't need this outside force. So it's an imaginary force based off of the way we observe the object. Uh, like I said, I just wanted to mention that quickly because that is a common mistake that people make, especially since there are so many things in media that you constantly see where they use the term centrifugal all the time. In fact, if you take one of those nursing classes in the medical field, you'll hear about centrifuges, right? That spin objects in order to separate them through high accelerations. It's the same idea. So there's this constant use of the term centrifuge, centrifugal, and it's all kind of like a big mistake. All right. So continuing on with this, question 14, object moving in a circle. Again, this one's really big plug and chug. So the answer for this one is B. You're really just using the equation 5 times 2 squared over 7. All right. Another one, question 15. The answer is going to be C. Same idea. We have the mass being 1,000. We have the speed being 20, and the diameter being 100. But of course, we don't want the diameter; it's the radius. So this is not going to be 100; it's going to be 50. So be careful with that. That's probably the only tricky part about this. Okay, 16. So now we're going into another AP question. This one is actually something that we're going to be talking about in a bit when we start talking about Kepler. So you want to make sure that you keep in mind what I'm about to say. So the idea here is, once again, if we're trying to find the tension in the string, we're looking for the centripetal force. So we have Fc equals mv squared over r. Now we know what the mass is and we know what the radius is. It's going to be m and r respectively. But what do we plug in for v? This is where we have to pay attention. They don't give us the speed. What they instead tell us is the period, how much time it takes to go around the circle. So we use the same equation we did earlier in the unit, where we said, okay, well, the speed is going to be distance divided by time. In this case, the distance is the circumference of the circle, which is 2 pi r, and it's going to be divided by t. We're going to take this and plug it into our equation over here. So this is going to be 2 pi r over t. And this is going to be squared. All right. This squared has to be applied all around. So it's going to end up being 4 pi squared r squared. I really hate that they use a lowercase m in the choices and an uppercase up here, but whatever, it doesn't matter. Divided by r. One r cancels out one of the r's up down here, or sorry, up there, and we end up with this answer. So it's going to be this one, 4 pi squared r over t squared. Like I said, this is going to play a major part when we start talking about Kepler's law. All right, this one. Oh, this one's actually a really interesting one. So they want us to figure out what the frictional force is between the adult and the child. So there's a few ways of going about this, and you might think that you should probably go about it through the conservation. It's not conservation. Sorry, doing centrifugal forces. The idea of like, oh, okay, well, we could find the normal force acting on the object because it's mv squared over r. We could do 1-1 method with that, and then ff equals mu fn. But it's simpler than that. Since both objects are going to stay pinned to the wall, both of them in the vertical direction will have a force of gravity going down, which is being balanced by the frictional force going up. And that's going to be true for both. So for both of these, the frictional force has to be equal to their weight. It doesn't matter what the centripetal, what we get when we do the centripetal forces. This has to be true, right? Because remember, when you do mu fn for an object that is static, you're getting the maximum value it could be, not the actual value it is, right? So what we do is ff equals fg. Because of the fact that the child is half the weight, then we know that the frictional force has to be half the force, right? They said that the force is F on the student. So if both these are F, then this has to be half F and half F. Here, okay, so this is actually pretty similar to the previous question. I think it was 16, where they give us all this information. They want the centripetal acceleration. So again, we're going to be doing v squared over r. We're going to replace v with 2 pi r over t squared over r. So we end up getting 4 pi squared r squared divided by t squared divided by r. 1r cancels out the r up here. Not like it matters because the radius is 1 meter. So plug in the numbers in, we end up getting that this is going to be 4 pi squared over 5 squared, or 25. All right, over here, object goes through the circle, it loses track right at point D, which is kind of a weird setup, but it doesn't really matter. And they want to figure out what path does the object follow. Well, if it loses track on D, that means the only force acting on it is going to be gravity. So if the car was still in contact with D, there would be two forces, a force of gravity going this way and a centrifugal force going this way. But because it loses track, contact with the track, then the only force acting on it is the force going down. Therefore, it's going to just go straight down. Because also the velocity is down. I should have probably mentioned that. Whenever you're asking like what is the path it ends up taking, you want to look at both the direction of the velocity and the direction of the net force acting on the object, mainly because of the fact that the direction of the net force is also the direction of the acceleration. So it's those two factors. What is the direction of velocity? What's the direction of the acceleration? And that tells you what the general motion of the object will be. And because they're both going down, the motion is going to be down. All right, this one. So this is a 1-1 question where they want to figure out what happens to the new speed. So they're telling us centrifugal force, radius, and speed. So we do Fc equals mv squared over r. The force is being doubled, the mass is staying the same, and radius is being doubled. You can already see here we get 4 equals v squared. So square root, we get 2v. So the speed is also going to be doubled. 21, plug and chug question. Answer is going to be B. So 2 times 8 squared divided by 1.2. Nothing crazy. 22, objects going around the circle. If the wire breaks at this point, what direction will it go? It goes in a straight line, so it's going to go towards point B. 23. Objects going around a circle, what direction are the velocity and centrifugal force? At this point, the centrifugal force is always pointing towards the center of the circle. If only I could draw a straight line. So boom and boom, those are out. And the velocity is always going to be tangent to the circle in the direction that it's moving. So since it's going in this counterclockwise path, the velocity will go straight up like this. So A. 24. So objects moving in a circle, they want to know what is the direction of the frictional force. Now, again, you need to be careful with the statement. While most of the questions in this unit will have the objects moving at constant speed, like I said, with a few rare exceptions, that's not always going to be the case. In fact, you will see, like I said, most of them will be constant speed, but there will be some questions where the speed might be changing. But also, when we get to another unit that kind of revisits circular motion, it'll be very common for those speeds to be changing. So here it says that it's moving at a constant rate. So the speed is constant, meaning the acceleration is constant. So the acceleration will be straight towards the center. So it's to the left. And then this one, again, pretty straightforward. They want the direction of the acceleration. Direction of acceleration always towards the center of the circle, so it's going to be to the east. All right, and that's it for these questions. If you have